So actually today, like if you want, then we can take extra class some other day. If we are not able, mostly 3 4 classes are there, then REC would be covered. If you want like some extra topic or that may not be on the website, you can tell I can teach, means I can say that. Okay. If you want, then let me know. Fine,
Okay.
we'll take care of that.
For RSC, sir.
RSC would be finished, no issue. RSC complete. After the psychometry, I would take equipment, various type of equipment, and how many types which we used for how much capacity. So that RSC would be covered in our scheduled classes. But apart from that, like for 1 or 2 classes, some topic doubt is there, that extra we can take. It would not be on the website actually. They would say only 1 hour 1 week. It is like that. Okay. So today, like only we are having 1 hour, because from 7 o'clock Jigar Bhaiya would be taking class, I think. So so today we will do three, like in we are doing at the end. Anyone remember what we are doing? Hello.
Sir, we did numericals problem.
Do anyone remember what we are doing at the end?
VCRS problems.
Not VCRS. Vapor absorption we have covered in the last class, and before that just we started the reverse Breton air or Bell-Coleman cycle, right?
Yes, sir. Yes.
So today two problem of Bell-Coleman cycle we will take, and one simple problem actually. Today we will be here for 50 minutes. So more than that we would not be able to do. So I would say like this problem you first read, that in the screen is visible, right?
Yes, sir.
First read this problem, and first this problem, then this problem. So you will come to know what is different here. Okay. So I think if you correctly you will able to do both these problems, then for the reverse Breton cycle you would be able to do each question. Apart from it, nothing will be there. Some efficiency here and there would be there, and that you can take care. So I think you can read this problem, and if along with me you also try. I will ask for the values, you will let me know. Okay. Read it, and then we'll start in 1 minute. If anyone if we want to solve, then I can also wait for 2 3 minutes, and then we'll start. I will read also. Then the aircraft refrigeration. It is the okay. The aircraft refrigeration system, air enters the compressor at a pressure of 0.1 megapascal and the temperature of 4 degrees Celsius. The compression ratio is 3. Isentropic efficiency, we will write the given data. TS diagram will make, then will it would be better. Which would be the inlet to compressor here?
2.
2. So P2 is given. P2 is given as 1 bar or 0.1 megapascal. And what is the T2? 277 Kelvin, right? And this is P lower 0.1 bar, 0.1 megapascal या 1 bar, and it is P higher. It is the how much? 3 bar, right? Is it clear?
Sir, this cycle starts from compressor. No?
That numbering you can take care. Okay. I have written here 2, so P2 T2 I have said. It is not much, so because we will follow the convention. We have said initially like inlet to the evaporator we are going to be taking as the 1. So same way we are doing. Okay.
Okay, sir.
Compression ratio is given as 3, so higher pressure would be the 3. And here isentropic efficiency of 72%. Compression isentropic efficiency is 70. 1 minute. This is 72%, 3 dash, and then it is cooled to temperature 55 degrees Celsius in cooler. Then what temperature is this 55 degrees Celsius?
T
Hmm? Which temperature is this? Hello? Am I audible?
yes,
Mhm. So anyone till it is then it is cooled to 55 degrees Celsius in cooler. Which temperature is this in the cycle?
T4.
T4 na? So T4 is 55 degrees Celsius. When you convert to the Kelvin, it will become 327 Kelvin, right? And in the cooler then expanded into the expander to 0 0.1 megapascal with isentropic efficiency of 78 degrees Celsius. So here again efficiency is there. So this is 1 dash, sorry, 1 dash. So we don't know the temperature here, 3 dash 1 dash. We know the temperature of T2 and T4, right? And P2 and P4 also we know. P4 is the 3 bar. So here you have to find the COP. What would be the COP here? Anyone? Hello? Hello?
Yes, sir.
What would be the COP here in the cycle? Refrigeration.
Desired effect
uh, by work input. What is the desired effect here?
3 into 3.567.
Okay, that is here fine. But in the cycle, in terms of enthalpy, what is the desired effect?
H2 minus H1.
Is it correct? H2 minus H1. Hmm? Here it will come to 1 dash, right? Because it is not isentropic.
Yes,
So H2 minus H1 dash, right? Hello.
yes, sir.
Then what would be the work input here in the cycle?
H3 dash minus H2.
H3 dash minus H2. So here you have to find these value for COP and then mass flow rate, then power consumption. So first we will find the unknown data. What is the unknown data here? T3, T3 dash, and T1, T1 dash. So for T3 we will follow the our relation like here what is the relation? T3 by T1 is equal to P3 by P1 to the power gamma minus 1 over gamma. Is it correct? Hello. Gamma is 1.4 here and P3 by P1 is 3. RP is given, right? Pressure ratio is 3. T1, sorry, not T1 here, T2, and here P2. So first tell the value of T3 from here. T2 is 277 Kelvin and P3 by P2 we know as 3 and gamma is 1.4. Tell the value of T3 and same way from here tell the value of T1. Here how will you do? T4 by T1 is equal to P4 by P1 to the power gamma minus 1 over gamma. So here T1 sorry T4 you know, T4 is 327. So from here tell the value of T1. Calculate it and let me know. First tell the value of T3, okay? Anyone doing it?
Yes, sir.
Okay, okay.
379.13 Kelvin. T2. T3.
379.13 Kelvin, okay. Some other person will also try and confirm this value. And what is the T1?
T1 getting 239.64 Kelvin.
9.64. Huh? Is it correct? Anyone? Anyone also trying or not?
Yes, sir.
Yes, we're trying.
Okay, okay. Confirm this value. Then, okay, just check this value and again next process. What will be the next process? With this isentropic efficiency, you have to find the actual value, right? Actual temperature value here. Sorry, here T1 dash and T3 dash. So for the compressor, what is the isentropic efficiency? 72 degrees Celsius, 72%. So isentropic efficiency of compressor would be, what would be the formula for that? Anyone? It is the
T3 minus T2 upon T3 dash minus T2.
so here you know the isentropic efficiency T3 and T2 also you know, and T3 dash you have to find, and T2 you know, right? So isentropic efficiency here you have to put as 0.72. So from here tell the value of T3 dash. One step I will do. T3 dash would be T2 plus T3 minus T2 divided by isentropic efficiency. So these both value would be same. So tell the value of this.
T3 dash getting 418.8 Kelvin.
What? How much?
418.8.
Okay. So it would be this value. Okay. So for the T1, it is the here I think I have made mistake. This would be the this way. So for the T1 dash, isentropic efficiency for the expander is 78%. So for turbine, what would be the formula?
T4 minus T1 dash upon T4 minus T1.
T4 minus T1 dash upon T4 minus T1. So here you have to find the T1 dash, right? How will you find here T1? It would be
T1 will be 258.89 or simply 9.
T1 dash, na?
Yes, sir.
1 minute. 4 minus T1 and here minus T4. Ulta 1 minute. This. So how much this?
258.9.
Hmm. Is it correct, right? Hello.
Yes, sir.
Hmm. Okay. So we got the all temperature values here. Now COP formula is this. So we can first problem is COP. So you COP we can find CP will cancel out from each term. So temperature we can write in terms of temperature also. So it would be a T2 minus T1 dash upon T3 minus T3 dash minus T2. So what is the T2 here? T2 is 277 and what is the T1 dash? T1 dash is this T1 dash 258.9. Next is T4. What is T4? 327 and not T4. So T3 dash. T3 dash is this
418.86.
418.8 and T2. T2 is where is T2? 277. So how much COP is coming?
0.1284.
0.1284. Is it same for others?
Point
सर टरबाइन वर्क में से तो
1264.
How much?
0.1264.
0.1264. Okay, this much is fine. Some here and there will be.
सर कंप्रेसर वर्क से टरबाइन वर्क माइनस नहीं करेंगे क्या?
Oh, sorry. This much is the compressor work and turbine work we have to also consider here. No? Here minus and this T4 minus T1 dash. Okay. So here we have to take the H4 minus H1 dash. So this is the only this term will justify the only compressor work here what we have to give, and here we have to also add the subtract the uh, expander work what we are going to get. So this would be the T4 minus T1 dash. So what will be the T4? T4 is 327 and T1 dash, this is the T1 dash we have calculated, it is coming 258.9. So now this also subtract from here, then what would the COP? This T2 minus T1 dash, how much it is coming?
Sir, overall answer is 2483. 0.2483.
0.258. This much is correct, yeah. So COP would be this. This is the simple problem actually. So here we have to consider the isentropic efficiency part only. And second question, what is the mass flow rate of air? So till here, any doubt is there? So for the mass flow rate, we have to see what refrigeration capacity is there. What is the refrigeration capacity?
3 into 3.5167.
Here means 3 into 3.5167. This much kilowatt. So for the mass flow rate, what will the refrigeration capacity is there, and what rate is there? So what in what rate it will take heat from here? Refrigeration effect would be here H2 minus H1 dash, right? So 1 minute. So here refrigeration effect would be H2 minus H1 dash. So 1.005 H2 would be T2 minus T2 dash, T2 minus T1 dash. So T2 is here 277, and minus T1 dash. T1 dash is this 258.9. So how much it is coming?
Finally, mass flow rate is coming 0.58 kg per second.
1 minute. 0.58 kg per second. Okay. So anyone calculated this refrigeration effect?
18.19.
10.19. So this much kilojoule per kg. So this much refrigeration effect with 1 kg. So you have to get the this much 3 into 3.517. 3.3 into 3.5167. This much of kilowatt you have to find. So for and in 1 kg you are getting this much. So when you divide with this, then you can get in 1 second how much mass flow rate of air you requires. Okay. So power consumption in kilowatt, that you can get. How you will get the power consumption in kilowatt? Any idea?
H3 dash minus H2.
Okay. Is it correct? How many of you are thinking it is correct?
M dot.
No,
Hello.
H3 dash minus H2 minus uh, H4 in minus H1 dash.
Is the correct, right? That much power you have to give. You can calculate that way also, and also another way, like COP of the system you know from here, right? 0.258, and refrigeration capacity also you knows, right? Hello.
Yes, sir.
So power input you can get from there also, refrigeration capacity divided by COP. Is it correct or not? Because refrigeration capacity is also in already in kilowatts, right? Is it correct or not? Hello.
Yes, sir, it is correct.
So two ways to calculate the power. One is the turbine work, sorry, compressor work minus turbine work. That is also correct. And another one is the refrigeration effect, refrigeration capacity by COP. So both ways are fine. Okay. So what is the power consumption?
40.89 kilowatt.
How much?
40.89.
Okay. You have multiplied with, is it correct?
I am getting 42.9.
Hmm. Okay, 40 to 45 it is correct, I think. In between anything, if you are, because some temperature here and there and COP, so it, 2 or 3 here would be there come. So how much? 42 here, I think 42.9 it is correct, yeah. So in this problem, you have to find the various temperatures, and when you know all the temperatures, you can find the values here. So if any like major doubt here, then tell me. Otherwise, same problem is another one, but different one. So there you will be come to know like, okay, this way also might come. So there one doubt will come, that we'll see. And if any doubt here, then let me know. Otherwise, we'll switch to next problem. So we should we go to next problem?
Yes, sir.
Okay. So okay, see the read this, and then we'll start. So it is also like in a Bell plant, air enters the compressor at 1 bar 10 degrees Celsius. It is then compressed to 5 bar. Air is then cooled to 25 degrees Celsius in the cooler. So same data it is given here also. So TS, let's suppose we will give 1 here, 2, 3 and 4. So this way is there, okay. So first we have to calculate the theoretical COP. So how will you do this?
1 minus RP to the power 1 minus 1 by RP to the power F.
Gamma you can take, okay. Here for first two problems you can take gamma as 1.4. So first problem is easy. Let me know the value of that.
%36.86%. Sorry, 0.3686.
COP.
Yes, sir.
Is it same for others?
Mm, 1.713.
Okay, two people to answer. First, how much? 0.36. Huh?
368.
Okay, another 1.7.
1.713.
Any other answer?
0.368.
So, any idea why, like how this 1.713, how you got?
Sir, formula 1 by RP for gamma minus 1 by gamma minus 1 I use.
Okay, so 1 by 6 to the power 0.4 by 1.4 minus 1.
High power.
Hmm? Okay, it is.
Ratio is 5.
Oh, sorry.
Lesser ratio is 5.
So how, okay, 1.73, and how 0.368 came?
सर वो गलती से ब्रेटन साइकिल का फॉर्मूला यूज कर लिया.
So exact correct answer would be what here?
1.713.
So 1.713 would be the correct. And also you can, okay, formula you remember, then fine. Otherwise, how you can calculate that? Find the temperatures T1, T2, T3, T4. and anyhow we have to find that them. So COP would be the what there from there, T1 minus T4 divided by compressor work T2 minus T1 and minus T3 minus T4. Correct? Is it correct or not?
Sir, COP for reverse Breton, Joule and Bell column is same.
It would be the same problem. So so like here what temperature you know, given data will write first P1 1 bar and T1 to 83 Kelvin and P2 is given as 5 bar and here T3 is given as 298 Kelvin. So let me know the value of T2 and T4. How T2 will come?
T1 into Rp to the power gamma minus 1 by gamma.
Rp to the power gamma minus 1 over gamma. And how T4 will come? T3 divided by,
X.
is it correct? So let me
Yes.
know the value of T2 and T4.
T2 is 448.22.
448.2 Kelvin, right? And what is T4?
188.15.
188.188. 188.
188.15.
Okay, 15 Kelvin. So now here we know T1, T2, T3, T4. So from here also we can get the COP. Okay, so both would be same. Might be little bit difference like decimal places. So it is okay. So here a refrigeration effect per kg. So what is the refrigeration effect here? H1 minus H4, right? Refrigeration effect H1 minus H4. So what will be the temperature we know? So Cp into T1 minus T4. So T1 is 283 and T4 is 188.15. So what would be the value here? Refrigeration effect per kg? It would be close to 9095.
95.32.
95.32 kilojoule per kg. Okay. Now how will you do this? That I want to know. Okay, this is first two problems and third one is sorry. Third one is like here compression and expansion are given as isentropic. Okay, is it correct? Hello.
Yes. Sir, क्या एक बार?
Here and first two problems, expansion and compression is given as the isentropic, like reversible adiabatic process. So, but in the third problem, compression is following like PV to the power 1.35 is constant. Means this value of n is given as for compression is 1.35 and for expansion is 1.3. Getting?
Yes.
Yes, sir.
So everything will change here now. Like T2 will change, T4 will change. Are you getting or not? Hello.
Yes.
So
Yes, sir.
So can you let me know the all temperature values T1, T2, T3, T4 in that way? T1 is given. T1 is how much? 283. And T3 is given. T3 is 298 Kelvin. So now I will change this T2 by okay, you tell. I will wait.
T2 is 429.54 Kelvin.
Okay, 429.54 Kelvin. And T4?
Finding
205.5.
205.5. In the same way, like just here you change the value of gamma. In place of gamma, you placed the value of n, right?
Yes, sir.
Okay. So now, what would be the work done for compressor here? Work done for compressor and work done for turbine. Per kg we can do Cp. Means 1 minute. H2 minus H1 and for the turbine H3 minus H4 and temperature we know. Can we do that?
yes, sir.
Okay. How many of you saying it is correct? Only one person. Okay. One another hint I will give. What is the work done for the open system for the polytropic process?
P1 V1 minus P2 V2 by n minus 1 into n. ऊपर.
Means n into n by n minus 1 into P1 V1 minus P2 V2, right? Means initial minus final into n by n minus 1. So for the compression it would be okay, it is same way, and for the turbine it would be the n by n minus 1 P3 V3 minus P4 V4. Would it both value H2 minus H1 and this value would be same? If you have no idea, then find both value. I think two times I have told the same thing initially, but you forgot now. Because this is the only one problem where you can commit mistake. Okay, that's why I am taking here time.
For isentropic and reversible, we can do H2 minus H1.
Here we can't do, right? Why?
They have not given reversible.
But it is open system, right? For open system air, we can write the work done as in terms of enthalpy difference or any other explanation you can give, because for open system enthalpy difference will show the work, right? Or some other assumption is there. I am asking you. I may not be correct here. Okay, like in terms of steady flow energy equation, I told it that time initially, right? Work done for closed system, and this is minus VdP. When it is correct, minus VdP.
Open system.
Open system is fine, and this is for only reversible process, correct?
Reversible and isentropic.
It is valid for everything, right? If isentropic is there, then we place in place of n we place gamma. It's right. Huh? It is valid
Yes.
for polytropic also, but work done for the sorry, open system, not closed system. Work done for open system, if it is reversible adiabatic, then we, when we steady flow energy equation we solved, then that time we saw minus vdp became dh, enthalpy difference, right?
Yes, sir.
So here what would be valid, this one or this enthalpy difference?
This enthalpy depends.
Why? Here it is adiabatic. Why is it adiabatic?
Isentropic given.
No, 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 no. Where isentropic is given?
In second point,
No, till
The
second
polytropic
question
process.
is different. Here written, assume both compression and expansion to be isentropic, having value of gamma is 1.4, Cp is this. This problem finished here. Third problem is different. Okay. So here compression and expansion have some different expressions. Pv to the power 1.35, Pv to the power 1.3. It is not adiabatic, right? Adiabatic gamma should be that exponent would be 1.4, right?
yes, sir.
And here 1.35 and 1.3 means it is not totally adiabatic. Adiabatic means heat transfer. Here heat transfer would be there, right? Because it is not 1.4. So if heat
Yes,
transfer is there, then dH would not be equal to minus VdP, because by deriving it we have given heat transaction as 0 there, right? In the formula, if you remember, heat transfer from the system we have considered 0. Then only,
adiabatic.
but here it is not so, right? So some heat transfer is there. So that's why we cannot go for this enthalpy difference. Whether it is open system, even though that we cannot go for open system, we can use this VDP formula, minus VDP. Are you getting it?
Yes, sir.
Sir, if it is gamma equal to 1.4, then H2 minus H1 is valid.
Then only simple problem. Then nothing. So here, because this it is a polytropic process, and like in the, I think I can show here also. This I can say. So here in the first class also I told, right? Work done for open system is this, and this came from only this is the general formula, and when we integrated it, it came, right? Hello.
Yes, sir. Yes, sir.
Yes.
And here assumptions are these, and again for open system is H2 minus H1, that I asked that time. How it came? That time you told steady flow energy equation we use, and when we consider this is adiabatic system, then Q we make 0, and no speed means velocity and uh, distance from datum is same, so that also will turn off. So work done for open system will become only H1 minus H2, correct?
Yes, sir.
So from here it is correct or not? Like if system is adiabatic, then open system can be the work done would be the enthalpy difference. But if system is not adiabatic, then it should not be like that. Then it would be the DH and plus what is the amount of heat transfer would be there. That also will come into picture, right? Now are you getting why we can't use that?
Yes, sir. Yes, sir.
So because that is the only one point there you conceptually can commit mistake. So that's why I am staying there. 1 minute.
Sir, reversible adiabatic, reversible adiabatic, and oblique isentropics. Means isentropic means reversible adiabatic, isn't it?
Reversible adiabatic is there, then it must be isentropic. Okay.
Yes, means if they have given isentropic, then we can use that formula, S2 minus H1.
Yeah, yeah. If here in like compression and expansion, they are saying reversible adiabatic or isentropic, then you have to consider a reversible adiabatic only. Okay. If it directly theoretical problem will come, then only you have to think like, okay, all reversible adiabatic are the isentropic. but all isentropic are not the reversible adiabatic. This sentence makes sense to you or not?
Yes, sir.
Huh. So that time you have to consider. Otherwise, if in problem simply written isentropic, then you have to consider okay reversible adiabatic. Okay.
And if there is just reversible mentioned or just adiabatic mentioned, then we can't use this delta H.
They have given adiabatic also, then you use. So if here they have directly written PV to the power 1.35, so it's mean like you cannot use that. Here explicitly you can see na. They will not trap you like it is isentropic. They will write and then say no, no, it is some internal irreversibility is there and it is compensated by heat transfer. If that would be there, then separately they will write that. If simple isentropic is written, then you have to consider reversible adiabatic. Nothing to think much. Okay.
Okay, sir.
So now can you tell work done for compression and work for the this turbine? So in here P1 V1 here volume you don't know. Do you know how you can do that? For per unit mass you can do that R into T, right? R into T1, R you can take as common, and T1 minus T2, T3 minus T4. Is it correct or not? Hello?
Yes, sir. Yes, sir.
So
Yes, sir.
work done for compression would be the N into R by N minus 1, T1 minus T2. So and work done for turbine would be the, here N would be the same for compression and turbine. Okay. So for compression take 1.35, for turbine take 1.3. So N R by N minus 1, T3 minus T4, and value for all you know from here. So just quickly let me know the value of WC and WT.
Sir, here we have written PV is equal to MRT form.
M we have taken as 1 here. Okay. We will write work done in kilojoule per kg, that format. Okay. Hello.
Yes, sir. PV is equal to MRT is ideal gas equation valid to all processes.
For here we have considered, right, uh, air you can consider as ideal gas in each problem, because whenever you are using this formula, this is valid for ideal gas only, right? T2 by T1 to the is equal to RP to the power gamma minus 1 over gamma. This is valid for ideal gas. If you are using in between, then it means you are considering ideal gas assumption. Anyone calculated WCWT? In here, you have to put N is equal to 1.35. Here you have to put
227.16.
how much?
227.16.
WC.
Yes, sir.
Okay, WC you are telling 227.16. Huh?
6.
Anyone getting the same?
Yes, sir.
सर आर को कैसे कैलकुलेट करेंगे?
Hmm?
आर को कैरेक्टरिस्टिक गैस कांस्टेंट को
That for air you can learn 0.287. Okay, remember it. Hello?
ओके सर.
Uh, anyone getting the same?
Sir, I'm getting different answers, sir.
How much?
162.
Any other person getting 162? Okay, so this 162.208, right? So this is the correct. Okay, just check the calculation. And same
सर यहाँ पे
हाँ
सर आई हैव डाउट सर
हाँ हाँ
सर यहाँ पे एन की वैल्यू जब डिफरेंट है तो फिर आर की वैल्यू डिफरेंट क्यों नहीं है
why r is the
सर
r doesn't depend on the process. Okay, r is the value for the gas, characteristic gas for gas it would be the constant, and this value of n will change with the process. Are you getting it?
यस
What is r? R is the characteristic gas constant, right?
यस सर
For a given gas it would be the same. What is this? R bar by molecular weight, right? Universal gas constant by molecular weight. So if you fixed the molecular weight, then why it will change with the process? Getting what I'm saying?
यस सर
So for air it would be the same. You just check the means what I'm saying. Just check the calculation and it would come the this value. Okay. So what is the turbine work?
114.98.
114.98 kilojoule per kg. So from here we know both values WC, WT, and W net you can get from WC minus WT. And what would be the refrigeration effect here? Refrigeration effect would be the H1 minus H4. So refrigeration effect would be the H1 CP would be the 1.005, and H1 minus H4, H1 would be the means CP T3 minus T4, 205.5. What is the refrigeration effect from here?
77.88.
77.88. Okay, correct. Fine. Kilojoule per kg. So the refrigeration effect we know, and W net would be the WC minus WT, and COP would be for cycle would be the refrigeration effect by W net. Okay. So what would the COP? Anyone? Hello.
1.65.
1.65.
1.68.
1.6. How much?
8 आ रहा है 1.68 सर.
Why? How much W net is coming for you?
46.345.
46.345. Okay. I think it should not be that much difference. 77.88. 1.68 is coming, right? 1.6.
हाँ सर 1. हाँ जी सर.
I thought 1.8 something you were saying. 1.68 is also okay. Okay. So like my main aim is like if problem is coming this way, okay, like there they changed the compression coefficient, expansion coefficient, and then how to tackle it. Now is it correct? You can do it this way, right? Hello.
Yes sir.
Yes, sir.
So today this one main problem is I want to tell. In reverse Breton, I don't think apart from that nothing will come. Okay, some reheating and that will add, but variation this variation is more than enough. Here they can change this only. So one simple problem in 1 minute we can do, and then we'll start in next Sunday. So like what is the heat rejection ratio? Here only one thing I want to tell. Heat rejection ratio. What is heat rejection ratio? Anyone know? Hello?
Heat rejected to heat taken.
Heat rejected by work input.
Huh?
QL by W in.
No, heat rejection ratio is the heat rejected in the condenser and heat absorbed in the here evaporator. Okay, QE and here Q condenser. So if like this is given, heat rejection ratio of condenser is 1.4. So find the COP. Can you do that? Okay, I will do once, and then remember that formula. It would be better, I think, to you. Let's suppose this is higher temperature. This is your system work input, and this is the quickly will do, and then I will stop. So here would be like a refrigeration effect would be this, right? And this would be the refrigeration effect plus W. So what would be the heat rejection ratio? This is the condenser. Is it correct or not? Condenser temperature. Hello.
Yes, sir.
I am just trying to give the formula in terms of COP so that you can do, because it's simply one liner problem will come for that. So that you, if you remember, then it would be better. Refrigeration effect plus W divided by refrigeration effect. So this will become 1 plus W by refrigeration effect. So W by refrigeration effect is what? 1 plus 1 by COP. Is it correct or not?
Yes, sir.
So it will become heat rejection ratio. So if heat rejection ratio is given, then you can find the COP of plant, correct? Hello?
2.5.
So simply you can do, right? It may vary, 1.5, 1.3, anything you can give. So 1.4, 1 plus 1 by COP. So you can simply find the 1 by COP as 0.4. So COP will become 2.5. Is it correct? Hello? Should we stop for today?
Yes, sir.
Actually, I think there is class from 7 is also there. So we'll stop for today. If like we need extra classes, then you can tell me. We can set in between also.
Okay.
Okay. So we'll stop for today here, and in
Okay, sir.
Sunday
Thank you.
same timing, 7, after 7 we'll meet. Okay.